when I was introducing to you why linear algebra is very important and very useful in machine learning, I mentioned that um, uh, one of the reasons was that the modern hardware, meaning the GPUs, can do the main operation very efficiently. And that operation is only two of them. There's addition and multiplication, which takes us to this operation actually. There is an operation called the dot product, and other name is the inner product, which operates on two vectors and gives you a scalar. We take the two vectors and we multiply each corresponding element and sum of the multiplications. That's it. And that's the core of every operation. So when a layer in neural networks processes its input, all it does is dot product. So this is one of the most essential operations in machine learning, and that's the part that touches the linear algebra. Why dot product is important for us? I can actually mention that the dot product is kind of what's going on in a human neuron, right? So on the top you see a human neuron that's connected to other neurons, and the operation that it does, it senses what it is coming from that, from each of the connections, and knows how much weight, how much importance it should give to these inputs, and gives its output to the next neuron. And we mimic these neurons with our artificial neurons that are doing nothing but weighted average of its inputs. So that's what dot product is. We take a weighted average of its input. We multiply input 1 with some weight, plus we multiply input 2 with some other weight, and we go multiply all of the inputs with some weights, and when we sum, there we go. We have our output. Mathematically speaking, this operation is, in fact, go to my dot product. So mathematically speaking, when we're multiplying two vectors, you see that there's a little transpose here, because when we put x and y next to each other, there are both column vectors in our definition, like the bold representation. They don't get dot producted to each other directly, just like in the scalar algebra. When you put in demonstration two scalars next to each other, it means that it's multiplication. AB is A times B. A dot B or X dot Y is represented with X transpose Y. So the reason for that is we will have the next one, Y, untouched as a column vector, and we're going to put the transpose, meaning the reshaped version of the other vector next to it. So I'm going to use my pens to show you, and I will keep referring to the same thing, because like when we make this L shape, reverted L shape, when they get together next to each other, we are talking about a dot product. When we're multiplying two vectors, as I mentioned, what happens is that the corresponding indices here, 135 and 246, the corresponding indices get together, 1 times 2, 3 times 4, plus 5 times 6, and we get, at the end, a scalar. So, and this scalar is going to be 44. Let's not question what this 44 means yet, but by the end of the first week, we will have a very good understanding of how this inner product is essential for using your face to unlock your phone. Because guess what? What's going on? There's an inner product happening. Your image is being taken and it becomes one of these vectors, and your phone has something, and then it calculates this inner product and looks at the number, resulting number. And if this number is good enough, I'm going to use the word good now, and I'm going to open up what good means. It is going to unlock your phone. So that's inner product. I would like to mention two things before I move on. Two things that are probably obvious. One, in order for maybe three things. Okay. In order for two vectors to be inner producted, as I mentioned, they have to come in form X transpose Y way. XY transpose is another operation that I will cover soon. When we take the inner product X transpose Y, a row vector sits next to a column vector, they like each other and they calculate the inner product. That was one. The second important aspect of this is that, you guessed it, their sizes have to be the same. Otherwise, you will have size mismatch and you won't have a dot product. And lastly, although it's an operation that operates on vectors, it emits a scalar, always a scalar. Some properties of dot product, as we mentioned, as we can actually mathematically show that X transpose Y is the same as Y transpose X, because what we're doing is we're going through each and every one of the elements of the two vectors, and we're just multiplying them and summing them. So in the end, as long as we have a row vector sitting next to a column vector, we have the same. Similarly, AX, if you scalar product one vector before an inner product, it doesn't matter if it is before or after the inner product. The third one is easily representable, easily provable. It's the rule that you can actually multiply the inner product. You can distribute your inner product into a term in parentheses as long as the sizes match. The last two are somewhat important. So like I'm going back between like practicality, I'm trying to go back between practicality and linear algebra. Sometimes we will want to have a summation of the entries. And as I mentioned, GPUs like vectors, they want to work with vectors and matrices, but the way for us to get the summation of the input, we can define you see the bold face on this one, we can define a ones vector. So this ones vector is a vector of ones, and when we calculate the inner product between 1 transpose X, what you do is just sum of the indices, because every index of the second vector gets multiplied with 1 and you get summed. The one that you will see almost every paper is when you do X transpose X. What you do is you calculate, you multiply everything with each other, so you take the square. So essentially you're taking the sum of the squares. So this is very widely used, and this is nothing but, you guessed it, it's your L2 norm squared. So when we are actually calculating the L2 norm, we're not doing the summation, this capital sigma and X of i's in vector programming and in our TensorFlow. What we're gonna do is X transpose X. So that's your L2 norm.